Ever glanced at a clock and thought, man, why can't I just rewind that thing? Time, it just keeps moving forward. But why is that? Well, that's exactly what we're tackling in today's deep dive. We're diving headfirst into the crazy world of quantum mechanics to try and figure it out.
And let me tell you, the answers we're looking for, they might just be even weirder than the question itself.
Listener, buckle up. We're cracking open a paper from the Foundations of Physics journal, and it's got some pretty wild ideas about this whole time thing. I'm talking about the decoherent arrow of time, entanglement entropy, even the very beginning of the universe itself.
It's all connected. And what's really fascinating is how this paper uses these concepts to try to explain one of the biggest mysteries out there, which is, why does time even have a direction? Why does it seem to go in one way?
Okay, you've definitely got my attention, but you've thrown out some pretty big words already. Decoherence, for example. What does that even mean?
Okay, so imagine like a glass of water. Now picture a drop of ink falling into that water. You see that ink spreading out, getting all mixed up. That's kind of like decoherence. Basically, in the quantum world, all these tiny systems are constantly interacting with their surroundings, and when they do, they become more entangled.
Entangled, like literally tied together.
Well, not literally, no, but
Yeah.
kind of, yeah. Entanglement is this really bizarre quantum connection that can exist between particles. And the crazy thing is, these particles can be separated by huge distances and still be connected. And as these systems get more entangled with their surroundings, they start to lose their individual, like their uniqueness. They become more chaotic, less defined. And that's what we call decoherence.
So it's like the universe is this giant glass of water, and it's constantly getting inkier as time goes on because things are becoming more and more entangled.
That's a great way to put it. And the really interesting thing is this process of things becoming more entangled, of the universe getting inkier, it seems to be really closely linked to this idea of the arrow of time, this idea that time only moves in one direction, like a one-way street.
Hold on, you're saying that because things are becoming more entangled, that's why we experience time moving forward.
That's the idea.
Yeah.
And this is where things get even more mind-blowing. The paper we're looking at, it suggests that this whole decoherent arrow of time, this idea that time moves forward because things get more entangled, well, it could be because the universe started in a very specific state, a state of incredibly low entanglement. They call this the Entanglement Past Hypothesis, or EPH for short.
Wait a minute, so you're saying the universe, it started out organized. That doesn't exactly sound like the Big Bang to me.
I know, right? It's a pretty counterintuitive idea.
Yeah.
We usually think of the Big Bang as this massive explosion of, well, everything. But what if, at least in terms of this entanglement stuff, what if things were actually much neater back then?
So instead of an explosion, it was more like a perfectly organized puzzle. And over time, the pieces have just gotten more and more jumbled up.
That is a fantastic way to visualize it. You're
Yeah.
getting it. But to really wrap our heads around what this neat and tidy beginning could mean, we've got to talk about entropy.
Entropy, right. The universe's tendency to get messier as time goes on.
Yeah, that's the basic idea. But it's not quite that straightforward.
Yeah.
To really get into it, we need to talk about 4 different kinds of entropy.
4. Come on now, you're just messing with me. I can barely handle one kind of entropy.
Don't worry, I'm going to break it down for you. First, we've got Boltzmann entropy, the classic, and also its quantum counterpart. Then there's von Neumann entropy. And finally, the star of the show today, entanglement entropy.
Right. Lay it on me. What are these different flavors of entropy, and what do they have to do with the arrow of time?
Okay, so let's start with the classic Boltzmann entropy. Imagine a box full of gas particles, just bouncing around. Boltzmann entropy is all about the number of ways you can arrange those particles in that box. The more possible arrangements you can have, the higher the entropy.
So more ways to arrange things equals more disorder equals higher entropy.
You got it. Now, quantum Boltzmann entropy, it's similar. But instead of gas particles, we're talking about the possible states of a quantum system. So the more possible states a system can be in, the higher its quantum Boltzmann entropy.
Gotcha. So both of those are basically measuring disorder, just on different scales. What about those other two?
Right. Now, von Neumann entropy, that one applies only to quantum systems, and it focuses on how much information we have about a system's state. The less we know about it, the higher its von Neumann entropy.
Interesting. So the less we know about something, the higher its entropy.
Exactly. And that brings us to the most interesting one for today, entanglement entropy. Remember that ink spreading out in the water, getting all mixed up?
How could I forget? You've officially ruined ink and water for me.
Uh-huh. Well, think of entanglement entropy. as a way to measure how much that mixing has happened, how much those different parts have become interconnected, all because of entanglement.
Okay, I think I'm starting to see how this all connects. So the more entangled the universe gets, the higher the entanglement entropy.
You got it. And that's where this paper's argument comes in. They suggest that the early universe, right after the Big Bang, had incredibly low entanglement entropy, meaning it was in a state of really remarkable quantum order.
So even though everything we know about the universe tells us it's moving towards more entropy, towards that ink in the water state, you're saying it actually started from this place of incredible order, and that's what this entanglement past hypothesis is trying to explain.
Yes, exactly. And it's a bold claim to make because it suggests something really, really profound about the very beginning of the universe and maybe even about the nature of time itself.
All right, well, you've definitely got my attention, but something tells me this is just the tip of the iceberg.
Oh, absolutely. This idea of a low entanglement beginning, well, it raises a whole bunch of fascinating questions. And believe me, things are about to get even weirder.
Okay, so we've established that the universe, it might started with this crazy low entanglement entropy, like this pristine quantum order, but it couldn't have stayed that way forever, right? I mean, look around, planets, stars, it's all a bit of a cosmic mess.
You're absolutely right. If the universe started in such an ordered state, how did it end up like this? That's one of the big questions this paper tries to answer.
So how do they explain that transition? Did the universe just wake up one day and decide to get messy?
Not quite. Remember decoherence, that process of systems getting all entangled with their surroundings over time? Well, this paper suggests that decoherence isn't just happening in the universe. It's like woven into the very fabric of space-time.
Hold on, run that by me again. Are you saying that space-time, like the very fabric of the universe, could be made out of entanglement?
That's one of the mind-blowing possibilities this paper explores. Some theories suggest that space-time, as we experience it, isn't fundamental, like it emerges from something deeper, and that something could be quantum entanglement.
Okay, my brain officially needs a break. So, entanglement. The threads holding the universe together, but then wouldn't that be a chicken and egg situation? Which came first, the entanglement or the space-time it's supposed to be creating?
You hit the nail on the head. It's a classic chicken and egg problem, and it's exactly the kind of puzzle the authors of this paper are trying to solve.
So how do they even begin to unravel that? I mean, where do you even start when you're questioning the very fabric of reality?
Well, the paper makes this really interesting comparison to another head-scratching hypothesis, the thermodynamic past hypothesis, or TPH. It basically says that the universe started with really low thermodynamic entropy, too.
So low entropy for energy and entanglement. Sounds like the universe had a thing for order back in the day.
It's a cool connection, right? Both the EPH and the TPH try to explain why the universe started in such an improbable, highly ordered state. Like something was special about those first few moments.
Like the universe tidied up right before the Big Bang, only to let everything go to chaos afterward. But I guess that chaos is what eventually created stars, galaxies, even us.
Exactly. That increase in entropy, that mixing up, it's crucial for creating the complex stuff we see in the universe today. The key takeaway here is that both the TPH and the EPH suggest there's some unknown, possibly fundamental physics at play in those very, very early moments.
Okay, so maybe we don't have all the answers yet, but it sounds like we're asking the right questions. I'm still hung up on this entanglement space-time thing, though. How can something that might come from entanglement also be the very foundation it's built upon?
The million-dollar question, right? To dig into that, we need to talk about factorization.
Factorization. Come on, now you're just using big words to sound smart. What is that in the quantum realm?
It's not as complicated as it sounds. Imagine you're trying to measure how messy a kid's playroom is. Do you look at each toy individually or group things together like building blocks, stuffed animals, art supplies?
Okay, I think I see where you're going with this. Got to organize the chaos somehow.
Exactly. That's what factorization is. Figuring out how to divide the universe, especially at the quantum level, so we can even start to talk about entanglement entropy.
So factorization is about how we draw these boundaries, these relationships in this vast quantum soup. But why does it even matter?
Because how we factorize the universe can actually change how we measure entanglement entropy.
Wait, seriously, you're telling me that the messiness of the universe, at least in the quantum world, it changes based on how we're choosing to organize it in our minds?
In a way, yeah. It's one of those weird loops in quantum mechanics. And it's a big challenge for this whole entanglement past hypothesis.
Yeah, I can see how that's a problem. If how we're slicing and dicing the universe changes our measurements, how can we be sure that low entanglement beginning wasn't just because of how we're looking at things?
That's a really good point, and it's something the paper spends a lot of time on. They actually suggest a few different, more flexible versions of the EPH, ones that aren't as sensitive to how we factorize the universe.
So they're looking for a version of the EPH that holds true no matter how we choose to categorize and organize the universe.
Exactly. They're looking for a more universal, fundamental expression of this idea that doesn't depend on how we carve up the universe.
That's a tall order. It's like trying to describe what a cake tastes like without knowing if it's cut into squares, triangles, or some crazy multi-dimensional shape we can't even imagine.
Now, that's a delicious analogy.
Yeah.
But that's what makes this research so exciting. It's pushing us to think outside our normal frameworks, consider totally new ways of understanding the universe.
Okay, so we've got these tweak versions of the entanglement past hypothesis, and
Mhm.
they're supposed to fix this whole factorization issue, this idea that how we organize the universe in our heads can actually change how we measure entanglement. But honestly, it feels like the more we dig into this, the more questions we uncover. Every answer just leads to another mystery.
That's the thing about being on the cutting edge of science, right? The more we learn, the more we realize how much we don't know. And factorization, that's a perfect example. It shows us just how much our understanding of the universe depends on our own perspective, how we choose to make sense of all the information out there.
I know, it makes you kind of dizzy.
Yeah.
If how we carve up the universe in our minds can change how we understand something as fundamental as entanglement, what does that even say about our ability to really grasp the true nature of reality?
Now, there's a question philosophers have been wrestling with for centuries. And this paper, it's rooted in physics, but it bumps up against some of those same deep philosophical questions. It suggests that we might need to completely rethink our approach to things like cosmology and quantum gravity if we really want to get a handle on the very early universe.
So, are you saying we need to just chuck out all our existing theories and start from scratch?
Not necessarily. It's more about being open to new ways of thinking, new ways of interpreting the data. Remember that wild possibility we talked about? The idea that space-time itself could be emerging from entanglement? Well, this whole factorization problem just adds a whole other layer of complexity to that.
Oh, I'm listening. How does factorization make the whole entanglement as the fabric of reality thing even more complicated?
Think about it. If space-time really does emerge from entanglement, like some of these theories suggest, then how can we use our concept of space, of distance and separation, to define the very thing that's supposed to be creating it? It's circular, like a chicken-egg problem, but on a cosmic scale.
Wait, so it's like saying I need to know how big my room is to know how much yarn to buy to knit a blanket. But the blanket is what the walls of my room are actually made of.
Exactly. It's a total mind bender. It really highlights the limits of our language, our concepts, when we're trying to tackle these fundamental questions about, well, the nature of reality itself.
So where does that leave us? Are we just stuck going in circles forever?
Not at all. See, just recognizing those limits is the first step to moving past them. And this paper, by highlighting the challenges of this whole factorization problem, it's pushing us to come up with even more sophisticated theories, ones that can deal with these crazy loops and paradoxes.
So it's less about getting those concrete answers and more about asking better questions.
Exactly. We've covered some seriously complex stuff in this deep dive, from quantum entanglement to the fabric of space-time. And yeah, maybe we didn't completely solve the mystery of time's arrow today, but I think we gained something even more important, a sense of awe and wonder at just how much we still have to learn about the universe.
Couldn't have said it better myself. It's both humbling and incredibly exciting to realize how much more is out there to discover.
And who knows, maybe someday, once we have an even deeper understanding of entanglement, of entropy, of the very fabric of reality, maybe we'll finally crack the code of time itself.
Until then, deep divers, keep those brains buzzing, keep asking those big, mind-blowing questions, and join us next time as we continue our exploration of, well, everything.